general relativity, step by step. I'm going to talk about geodesics near a black hole. Near a black hole. It's a little bit fiddly this, but I'm going to do it anyway. Now the equation we had for geodesics was x double dots alpha plus, and this is from screencast 48 through 51, I think. Christoffel symbol alpha beta gamma x dot beta x dot gamma equals 0. Well, that's actually a pain in the neck to evaluate. So what I'm going to do is I'm going to go back a step and I'm going to talk about calculus of variations when I'm going to have an extremal path for f. And what we're going to do is we're going to evaluate f as g alpha beta x dot alpha x dot beta, where a dot equals differentiation with respect to proper time. So what we had last time was that, I'll just write in my notation explicitly, f was equal to some function of t and xi and xi dash. And the Euler Lagrange equation, Euler Lagrange, what did that give us? That gives us that d by dt of di f by di xi prime minus di f di y, no, it's not y, it's an x. xi, you'll see y in the literature for reasons that aren't entirely clear to me. Sometimes you have t as the horizontal axis of your graph, sometimes t is your independent variable, and sometimes it's x. And it's difficult to have t and x and y, so quite often you'll see x and y dash as your three dependencies of f equals 0, and that's the Euler Lagrange equations. What I'm going to do is I'm going to use this equation here and substitute for this term here. But what I want to do is to talk about df by dt. Remember that f is a function of t and xi prime, so I can decompose its dependency into a curly t plus an xi prime di f di xi, because this guy might be changing in time as well. Well, it is. Plus xi dash dash di f di xi dash. And all I'm doing is I'm pointing out that this function here, f, if I want to know how it changes with respect to t, well, I've got to account for this term and this term and this term all together, and that's how to do that. Now what do I do? What do I do now? I make the observation that I'm going to go into red here. Red. I can make the observation that this guy is equal to that guy there, so I can just use the left-hand side of the equation. Oh, I could say that the left-hand side equals the right-hand side. Let me just change it to that. Equals that. There we go. So I'm just going to substitute for that and see what happens. Let me pinch in a little bit. Go back to black. Black is here. Equals di f by di t plus xi dash, and then substitute d by dt di f di xi dash plus this term here, xi dash dash di f di xi dash. There we go. Equals di f by di t. Oh, have I said x? No, that's right. Plus d by dt of xi dash di f di xi dash. Now why is that? All I'm doing there is I'm effectively factorising this term here using uv dash, total derivative term, equals u dash v plus uv dash. So I differentiate this xi, and that gives me that term there, times df dxi. Differentiate this one, with respect to d by dt, and we get that term there. That's nice, isn't it? So that's df by dt. It's a little bit tricky to get to grips with what's going on here. What I'm doing here is I'm just expanding f in terms of its derivatives with respect to t here, but I'm using the Euler Lagrange equation. So this is a restatement. This statement here is a restatement of the Euler Lagrange equation. And I can do something a little bit clever here. I can say it's d by dt of f minus, what I'm going to do is to take this term here over to the left hand side. xi dash df dxi dash equals df by dt. Is that right? Yes, df by dt. Okay. So if df dt equals 0, which it very frequently is, quite often you haven't got any direct time dependencies. We'll see what it means physically in a few minutes. If df dt equals 0, if that's the case, then d by dt of f minus xi prime df dxi prime equals 0. And that tells me that f minus xi dash df dxi, sorry, that's downstairs, dash, equals a constant. That's quite nice. And this is incredibly useful. This is a much more straightforward way of thinking about the calculus of variations. If this condition here is met, and we'll see, I think I better stop this screencast, it's already longer than I wanted. We'll see in the next screencast how useful this technique is in the context of relativity. But for the moment I'm just going to marvel in this result here. What we've got here is the Euler Lagrange equation here. I've expanded f in terms of its three components. I'm substituting for one of the terms in this expansion using the Euler Lagrange equation, and then I'm sort of factorizing it to have this constant of integration here, which is quite nice. And we'll see how it's used next time. I'm going to stop there, and I'll use it next time to do something clever with. Stop.